Hello, everybody, and welcome to our very first sound PowerPoint presentation. In this first installment, we're going to take a look at what sound is, what creates it, and what's it sound like when it makes a sound. I'm going to go over there. Hey, let's start, shall we? What is sound, you ask? Sound is a vibration. It is essentially a vibration that you can hear. Hey, look, it's a bold-faced underlined word, and write it down. Okay. Sound. You know, because when matter, it moves back and forth, back and forth, back and forth, at a rapid rate, it is said to vibrate. You know, like a ruler. What? You're looking at me funny. Like, what are you talking about, Mr. Eichler? Seriously. No, really, you've never done this before, right? You got the ruler, right? And you got it on the table, and you do this. Vibration. Watch it. It's going up and down. Vibrating. Spare ruler. Later, I'll play Beethoven's Fifth. Vibrating back and forth, it creates sound. That's what it is, right? As vibrations travel through matter, it causes a shift between the molecules. Molecules are those little tiny little bits of things that make up everything. In some parts, it causes compression or squishing, and in other places, it causes what's called refraction. That's a great big huge word. You don't really need to know it, but it's a cool one if you do know it, because then you sound really smart. People go, hey, wow, that guy's smart. If you look at our little coils and springs here, you can follow this wave as it goes through. And in front of that wave is the compression, and behind it is the separation or the refraction. And this is what makes up a sound wave. The compressions, bold-faced, the compressions are regions of high pressure where the molecules are squeezed together. Refraction, I lied, you do need to know that word. Refraction is where there is the least amount of pressure in between the molecules. Now, as you look at this tuning fork vibrate, the heavy dark areas are where the molecules of air are being pushed together. The lighter areas are where they are being spread apart. I know what you're saying. Gee, it'd be really great if you had a tuning fork here. I got the box set, actually, because, you know, it's a box and it's a set of them, and it's, never mind. This tuning fork. Tuning fork is in this case, piece of aluminum, and they are measured to a precise length and set to vibrate at a certain frequency, or when they go back and forth. And you can't hear anything. But can you hear it now? I could get a job working for that cell phone company. Can you see it moving? Kinda buzzing, just a little bit back and forth. This one's shorter. Right? When they're going back and forth, they're vibrating. And when they're vibrating, they're pushing the air back and forth, right? It is that compression that creates sound, that creates vibration. The more vibration, the faster it vibrates, the higher the pitch. But we'll get into that in a second. The results in the vibrations traveling in waves, sound waves. Sound waves are quickly moving areas of high and low pressure. When we talk, we are creating sound. Our vocal cords right here in our throats, see them? They're vibrating. They're doing this. And when we speak, we blow air over those vocal cords through our throats. This creates vibrations. Our mouth forms the sounds, and we can communicate to each other. Sound waves result in the movement of energy through any form of matter. And it's true, sound will go through just about anything. Just about. You can see here that where the areas or the molecules are dense together, pushed together, that is compressions. And over here, where the molecules are all spread apart, that is where we're having our little rarefactions. The more dense the matter is, the faster sound will travel. And if you don't believe me, have you ever been swimming? You know, that thing where you get in the water, right? And your buddy is way down at that end of the pool, and you're way over there at that end of the pool, and they scream underwater. You can hear them like they're right next to you. That's because in water, sound travels much faster. You want to try an experiment right now? Hit pause on this. Not yet, wait. When I say go, hit pause and go put your ear on top of the table. Just like this. And then lightly, lightly scratch the table. Lift your head up. Can you hear it? Put your ear back on the table. It'll sound like it's really loud. Go ahead, hit pause now. Try it, really. It's cool. It's science. I'll wait. Okay, you back? Air is not dense. Steel is really dense. Sound travels through the air at a rate of about 340 meters per second. Just about, give or take. Another fun little thing you can do with sound. Hi, I'm big again. When you hear lightning and you see the flash of lightning, start to count. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. For every 5 seconds you can count. That is roughly, approximately, not exactly, but approximately 1 mile away. True story. So for every 5 seconds you count, that's 1 mile away that lightning bolt was from where you are. So if you see the lightning and you count and you get to 7, well, it's about 1 2/5 miles away. And then you see another flash and you count and you get to 3, that means it's getting closer. But if you count and you get to 12, that means it's getting further away. Good to know, right? That's all I got for round 1. Thank you all for joining us. Put your ear on the desk. Try it. I'm not kidding. It's cool. We'll see you next time. Thanks for joining us.